So far, we've separately considered systems with external or internal resistance to mass or heat transport. But generally, both resistances must be considered for real systems. Let's see how we could treat combined internal and external resistance to mass transport for a first-order reaction in an isothermal flat plate. A mole balance on A in a thin slice through our slab gives an expression that looks like this. If we divide through by the area available for diffusion times the thickness of this differential slice, and then take the limit as delta x goes to 0, or the slice becomes infinitesimally thin, we arrive at the following differential equation. We can write the flux as a function of concentration using Fick's first law. And plugging this expression into our differential equation, we come out with a second-order differential equation that describes concentration as a function of position inside the slab. We can non-dimensionalize this differential equation using non-dimensional parameters for concentration and position. So we'll label these psi and omega. To obtain this differential equation shown here, which depends on the Thiele modulus. For a first-order reaction in our flat plate, the Thiele modulus is equal to the half thickness of the slab times the reaction rate constant divided by the effective diffusivity of A through the slab, all to the 1/2. So thus far, this has been identical to the process for finding the concentration profile in the absence of external diffusion limitations. But here, the only thing that's going to change is essentially our boundary condition. So we could either describe this as a surface concentration that depends on the mass transport coefficient through the boundary layer and a bulk concentration. So essentially, as we've done before, solving the concentration profile through the boundary layer. Or we can set a boundary condition that equates the flux of A going into the plate, so the internal mass transport, to the flux of A reaching the plate by diffusion through the boundary layer. Solving this problem through either of these means, we can come up with a concentration profile that looks like this. Where here we've introduced one additional dimensionless parameter, the Biot mass number, and this is equal to the half thickness of the slab times the mass transport coefficient through the boundary layer divided by the effective diffusivity of A. So this quantifies the relative rates of transport outside of the slab relative to through the slab. Similarly to how we did for internal resistance to transport, we can define a new overall effectiveness factor. So we'll label this omega. So this will be equal to the rate at the actual conditions at the active sites within the slab divided by the rate we would observe if all active sites were seeing the bulk concentration and temperature. The overall effectiveness factor will be a product of an external effectiveness factor and an internal effectiveness factor. So for our flat plate geometry with a first order reaction, the overall effectiveness factor would be equal to this expression. So here we have two terms, one associated with the internal effectiveness factor, so this looks identical to the expression we've seen before, and this second term is the external effectiveness factor. So we can describe concentration profiles and temperature profiles for systems that are non-isothermal using the same sort of approaches that we would for treating internal and external resistance separately. So for this system, we might have a concentration profile that looks like this. We have a constant composition in the bulk fluid. We have a linear decrease in concentration of A through the boundary layer, and then we have some depletion of A within the catalyst pellet. So here we've seen how mathematically we can treat systems in which there is combined internal and external resistance to mass or heat transport.